Welcome dear students once again into the class of number theory, and in the previous three videos we have done a lot about continued fractions, and in this video we will continue with those fundamental concepts of continued fractions. So what the next theorem says is, if Cn is the nth convergent of simple finite continued fraction a0, a1, a2 and so on, an, then c0 is less than c2, is less than c4 and so on, is less than, on the other side, c5, is less than c3, is less than c1. That means the sequence C to n is monotonically increasing, and the sequence C2n plus 1 is monotonically decreasing. Moreover, every even nth convergent is less than every odd nth convergent, and moreover C2p is less than or equal to limit of Cn as n approaches infinity is less than or equal to C2p plus 1. That means the sequence Cn is convergent, and the point where it converges is greater than or equal to every even as convergent and is less than or equal to every odd convergent of the simple finite continued fraction given by a0, a1, a2 and so on up to an. Now we are moving on to the proof of this theorem. So let us see how to prove it. Since we are to deal with either even or odd, so what we are to do, we are to deal with the convergence having difference of 2. So that means Ci minus Ci minus 2. We know that Ci is Hi over Ki minus Ci minus 2 is Hi minus 2 over Ki minus 2. What are these Hi's and Ki's? You must know if you have seen the previous three videos. Now, taking LCM, you will get Ki minus 2, and here you will get Hi, Ki minus 2 minus Hi minus 2 into Ki. And in the previous video, you have seen that the value of this numerator is minus 1 raised to the power I, Ai. So it is minus 1 raised to the power I, Ai divided by Ki minus 2, not 1, sorry, 2. Now, we'll take the case separately, that means for the even convergence and for the odd convergence. If your I is 2n, that means if your I is an even number, what is going to happen here? You will get C2n minus C2n minus 2. You are substituting I to be equal to 2n is equal to, here minus 1 raised to the power 2n, minus 1 raised to the power even will become 1, and you will get A2n divided by K2n into K2n minus 2. Since A2n is positive, K2n is positive, K2n minus 1 is positive, so this quantity is greater than or equal to 0. C2n minus 2 is greater than or equal to 0, means C2n is greater than or equal to C2n minus 2, or you can say C2n minus 2 is less than or equal to C2n for every n. Now put n is equal to 1, 2, 3, 4 and so on. Putting n is equal to 1, what you are going to get here, C0 is less than or equal to C2. Then put n is equal to 2. So C2 is less than or equal to C4. This C2 is less than or equal to C4 is less than or equal to C5 is less than or equal to C6, sorry, not 5, because we are dealing with even convergence. So this is the one result. Again, take I to be equal to 2n plus 1. What will happen? If you take I to be equal to 2n plus 1. Taking I is equal to 2n plus 1, you will get here C 2n plus 1 plus C 2n minus 1. And here minus 1 raised to the power 2n plus 1 minus 1 raised to the power odd will become negative. So it is minus. This is positive, this is positive, this is positive, but there is a negative sign. So this quantity is less than or equal to 0. So you can say that C2n plus 1 is less than or equal to C2n minus 1. And now once again, take n to be equal to 1, 2, 3, 4 and so on. Taking n to be equal to 1, start from here, C1 is greater than or equal to C3. And now put n is equal to 2. So C3 is greater than or equal to C5 is greater than or equal to C7 and so on. So that means the first part of the theorem we have proved that C0 is less than C2 is less than C4 and so on like this. So this part we have proved. Now we'll move ahead because we have to show that every eventh convergent is less than every odd convergent. For that, once again start with Ci minus Ci minus 1 this time. Ci is Hi upon Ki and Ci minus 1 is Hi minus 1 upon Ki minus 1. Once again, taking LCM, we will get Ki minus 1 in the denominator, and in the numerator, you will get Hi Ki minus 1 minus Hi minus 1 Ki, and the numerator, you have seen in the previous video that the value is minus 1 raised to the power I minus 1 upon Ki minus 1. So this is the value. And now what the result you are going to put I to be equal to 2p or 2p plus 1 or 2p plus 2, anything. So taking I is equal to 2p, here you will get C2p minus C2p minus 1 is equal to, here you are taking I to be equal to 2p. So 2p minus 1 odd. Minus 1 raised to the power odd is negative. Negative divided by positive is negative. So this quantity is going to be less than or equal to 0. So that means C2p is less than or equal to C2p minus 1. But that is for a particular p. We have to show that every even convergent is less than every odd convergent. So that means in general we have to show that C2p is less than or equal to every C2q minus 1 or 2q plus 1. So for that, this part we have shown that C2p is less than or equal to C2p plus minus 1. Now, take two different integers p and q. Let p and q be any two different positive integers. So three cases may be there. Either p is equal to q, or p is less than q, or p is greater than q. If p is equal to q, simply you have C2p is less than or equal to C2p minus C2p minus 1, which is in fact C2q minus 1 because p is equal to q. If your p is less than q, if your p is less than q, what you are going to get that C2p. Now 2p is even. For even, you know that your C2p is less than C2p, or you can say that C2p is less than or equal to C2p minus 1, C2p minus 1, and 2p minus 1 is odd. 2p minus 1 is odd, and for odd you know that C2p minus 1, if your p is less than q, p is less than q, I'll have to change, a little bit change is required here. C2p is less than or equal to C2p plus 2. C2p plus 2, and C2p plus 2 from here is less than or equal to C2p plus 1, and C2p plus 1 is less than C2p minus 2q, sorry, not p, q. So it is less than 2q minus 1. And the third part can also be proved on the same lines. So in general, you have proved that every even convergent is less than every odd convergent. If you have any p, any q, then your C2p here is less than every odd C2p plus 1 or C2q minus 1 or C2q plus 1, you can say anything, because you just want here an odd suffix. It may be 2q plus 1, it may be 2q minus 1, but every C2p is less than every C2q plus 1 or every C2q minus 1. Even you can write here C2p is less than C2q minus 1. As we will be requiring, we will use the result. Now, we are to show that limit of Cn lies between these two. But first we will have to show that Cn is convergent. C2n is monotonically increasing and is bounded above by C1. A sequence which is monotonically increasing and bounded above is convergent. So C2n is convergent. One thing is clear, that this sequence is convergent. Similarly, C2n plus 1. This sequence is monotonically decreasing and bounded below by C0. A sequence which is monotonically decreasing and is bounded below by some number is once again convergent. So your C2n plus 1 is also convergent. Both these sequences are convergent. Now, C2p, take any n, then this n is either of the form 2p plus 3 or 2p plus 4. That means either odd or even. Either this n is odd or this n is even. So what will happen? Your C2p from here is less than C2p plus 2, and C2p plus 2 will be less than C2p plus 4. If it is n, so it will be less than Cn if your n is this one. And C2p plus 4, that means this one is less than C2p plus 5, because every even convergent is less than every odd convergent, and this C2p plus 5 will be less than C2p plus 1. And if your n is 2p plus 3, you start from the other side. C2p plus 1 is greater than, remove this portion, then your C2p plus 1 is greater than C2p plus 3, and C2p plus 3 is greater than C2p plus 2, and C2p plus 2 is greater than C2p. So removing these parts from here, remove these two parts, what you are going to get is that C2p is less than Cn is less than C2p plus 1. And now taking limit as n approaches infinity, since both even and odd are convergent and they are converging to the same point, as one is increasing and bounded above by the odd, and the odd is monotonically decreasing and bounded by the even convergent, so their point of convergence will be same. So applying limit now, what you are going to get, that C2p is less than limit of n approaches infinity, Cn is less than C2p plus 1. So this is how to prove that this theorem. This was a little bit complicated theorem, but is not at all difficult. I think you will understand this theorem very well and will be able to reproduce it if it appears in your examinations. So we'll move ahead with the periodic continued fractions in the next video. Till then, thank you once again.